forwarding
yeah.
computer. Okay, so with this linked list package, you can remove this package, circular linked list. That's fine. If it's not removed, then what you need to do is put it into a folder called circular linked list. That's all.
Okay.
So when it was just simply because of that's how I organized it when I initially created this assignment. So implements iterable. You'll see that later in the assignment. Okay. And again, as you mentioned, there are videos where I've gone over this in previous classes, like 2168. In 2168, I give the students an option of doing this one, which is easier, and another one that's harder called the solitaire encryption. I've done that before during the summer. That was not during the summer. For this class, doing it in this class is just not nice to students who have not had any programming experience because it makes the assignment so much larger. Okay, the entire point of this is to solve the Josephus problem. That's a famous math problem named after a famous or relatively famous Jewish historian from the early 0th century, actually. He was a Jewish priest and a general who basically had a war band that led to a revolt against the Romans, and it went pretty much exactly the way that almost all revolts against the Romans went, which was terrible. Okay, so as a result, he got captured, and he made this amazing prediction that the general who had captured him was good at generaling, and therefore, because he was so good, he was obviously ordained to become emperor. And wouldn't you know it, he eventually became emperor, and so he eventually got granted his freedom. He then proceeded to become he proceeded to Romanize and write a lot about the Jewish history of the time, which is really kind of important to non-Jews, because the Jewish history of that time is Christianity, because there's a bunch of stuff going on during that time, right? That's the 0th century. That's that time. So that's when basically, so it's at that point, Christianity and Judaism still haven't kind of diverged on their separate paths yet. So he actually is so it's the kind of contemporaneous history of what Jews were like during that time, and therefore what early Christians were like. So and it's a non-biblical source, so academics love that.
Yeah, that's really cool.
So yeah. Anyway, the math problem is about basically I've got a kid next to me. So let's say it's about playing a game, and every other person you get in a ring, every other person basically becomes out of the ring, and you want to basically be the last person standing in this ring. Okay.
Like like eeny, meeny, miny, mo kind of thing.
Eeny, meeny, miny, mo, just like basically 1, 2 is out, 3, 4 is out, 5, 6 is out, 7, 8 is out. And then it wraps back around. Like, so say you've got 42 people in the ring, 41, 42 is out. But now you keep going. 1, 3 is out, 5, 7 is out, 9, 11 is out. So where do you want to be to be the last person standing in this ring? Now, if you give me a second, I can actually give you an answer, the generalized answer for the Josephus problem. Okay. The generalized answer for the Josephus problem is, you can find it over here. Give me 1 second. I got to pull it up on a window. Boom, boom, boom. Here it is. So it's got a beautiful Wikipedia article about it. And the generalized solution is this mess. Okay, this equation. Given n people in the ring and you're removing every kth person, then this is where the answer. This is the answer for where you want to stand. Wonderful, right? That looks nice and easy and digestible, right? But we're not in a math class, and we're not even even though this is a programming class, this is not for computer science. For computer science, some people might be moderately interested in that, but honestly, no. The entire point of this exercise is less about the math and more about, okay, how can we simulate this to solve this instead? Instead of trying to do complicated math, let's actually just physically model this and run through it. That's actually a really good way to end up to handle a lot of things. A lot of things in programming when the math looks complicated. In fact, they have a fancy term, numerical analysis in mathematics, when we go, these differential equations look way too hard. Instead, we're just going to approximate our answer and it to as close as possible. So modeling things or approximating things, different strategies we have to avoiding math, essentially. So the way we do this instead is that we make a linked list. Every person's represented as a node, and we use the remove method to remove that. We use the add method to build it up. So your task is basically complete the constructor. Believe it or not, you can simply leave it as is. Otherwise, you just simply set the head and tail to null, the size to 0, because that's what it initializes to. This is going to work. This is just simply making you copy down. Just so you as a warm up, it should work exactly as the same way it should in my videos.
So get node works the same way as the doubly linked list, you'd say?
As the singly or the doubly. This is going to be a singly linked list because if it's doubly, that means you have twice as many places to make mistakes.
So this is going to be, it's basically you're saying
it's a singly linked
similar.
list. So so this is a singly linked list. The difference is from my video is that it has a tail and it loops around. And the tail always connects to the head. Okay, so the first part, it having a tail means it has the same five cases that the doubly linked list has. Got it? So and I've listed all those cases here. I'll get to that in a second. And the other thing again is you have to have a single line that says the tail points to the head whenever you modify the head or tail. Okay, so let me go through these methods really quickly again. Attach a node to the end of the list. This should always return true, not false. We use the reason the add method returns true is that's just standard practice in Java, that add should return that when you say add something and I don't care where it goes, okay, as opposed to add something at a specific location. In Java, when you say add something and I don't care where it goes, you return true or false. In a list, you're always going to return true. Why? Because the true or false represents whether or not you're successful at adding it. And in a list, you're always successful at adding it or you blow up the program because you ran out of memory. So so you always return true as a result. So just simply switch this false to true. Okay. So in this case, right, we have now over here, we have 5 cases. Okay. The add to anywhere else, this is the one that uses the get node. Okay. Add to out of bounds, that's exactly the same as what you saw in the videos, right? Just making sure it's out of bounds. Just make sure you have your less than greater, less than sign or less than or equal to appropriate for whether it's the add or remove, right? So go back to the videos and check that. That's one of those mistakes. By the way, I recommend making sure that you get the add method working before anything else and kind of test it the way I watch how I did it in the videos, how I slowly built that up and tested that. Okay.
Yep. I
will get to that in a second. Adding to an empty list. Why? We keep this separate. The idea here is I don't want you to make nested if statements. Nested if statements makes the logic a bit too convoluted. I don't like that. So here are just kind of separate. This is an if statement, and then these 4 are if-else statements, right? If, else if, else if, else. Got it?
Yep.
That way, okay? Adding to an empty list. That's easy. You just simply check if the list is empty. How do you do that? Check with the size. What is the size when the list is empty? That should be obvious. I'm not going to go that far and let you know. Adding to front. You figure it out if it's the front by checking what index it is. You check, how do you know if you're adding to the end? You check what index it is. All 3 of these functions in both all 3 of these cases in add or remove, they modify what the head or tail is. So when you're done doing whatever manipulation you need to, you do one more line. You say the tails dot next, it now needs to point to the head. And that just simply reinforces that the list needs to be circular. Okay. Now, that's the only difference really. So basically you can use the same code that I used in my videos for the doubly linked list, except you ignore all the stuff about having a previous, okay? And you just need to use that, make sure the tail points to the head in there. Okay, same thing with the remove. It's the same thing with the remove. The same case, only the cases are removing the only thing in the list. In other words, if the list is size 1, that's its own special thing. Because why? Because you got to make sure you get rid of the head and tail. You got to make sure that the head gets set to null, the tail gets set to null. Removing the first thing in the list, that means removing the head, right? Removing the last thing, that means you're removing the tail. Again, you figure that out by knowing the index. Again, it follows the same exact structure as my linked list video. So this is one of those assignments where it does look a lot more complicated than it actually is. The main goal of this assignment is to make sure you are comfortable with this idea that it is a variable on the left. Sorry. You take the memory location on the right side of the equal sign, and you store it on the variable on the left side of the equal sign.
Yeah.
Making sure you understand what that equal sign does. That is the entire purpose of this exercise, the entire pedagogical point of the linked list. It really emphasizes how that equal sign works. Okay. Now, this stuff, toString, useful for debugging. I'm not kidding here. I wrote you the toString method, and it's very useful because I deliberately designed it to crash if your linked list is broken. Okay, it will usually crash if it's broken. Okay, so if you print if you try to print out the list and it crashes, guess what? It's probably not my fault. It's probably your fault. So, yeah. Now the iterator, oh, that's beautiful. I made it for you. It is wonderful. Okay, and the idea here is that you don't need to worry about has next. It's a circular linked list. There's always going to be it's always going to have another item. The way it iterate works is that it iterates for you. It iterates over the list for you, keeps track of the index for you and everything, so you don't have to think about that. So calling next the first time will get you index 0. Calling next the second time will get you index 1. Calling it next the third time, index 3, and it will just always wrap around based off the size, right? It's gonna take care of wrapping around for you. Remove removes the last thing that was called. So if you wanted to remove index 1, you would go .next, .remove. So you use this in the final step, by the way. Oh, and I'm particularly proud of this. The way it removes something is that it calls your remove method to do it. Okay. So the PDF goes over the best way to do that for yourself. How to use it. But again, .next, .remove makes it work really, really well. Specifically, what you want to do is that to remove is that when you're going through the puzzle, what you want to do is and this is what happens in the main method. The main method is going to be very short. While there's more than one person in the list, make k.next calls, okay, followed by a single remove call. So if n is equal to 2, and so you have a while loop with a for loop inside of it.
Can you walk in water and stuff?
Ask mom. Sorry. All right. So in your main method, again, that's where you just run it. You don't necessarily, and I wouldn't worry about taking an input. You could simply say int n is equal to this, int n is equal to however many, int k is equal to however many, and you could just start from there, right?
Okay.
And then modify it to whatever you need to test about the values of. The only thing I need to warn you about is that you have to add the items before you create your iterator. Okay, so basically it should look something like this: circular linked list is equal to new circular linked list. Let's make sure the generics are in there, right? It's a generics, so it should be integer, right? And then the other thing we need to do is we will simply, I'm going to hand wave that. This is for you. Add your items. Okay. And then we create an iterator. The way we do that is very simple. We say iterator. And because, of course, it's going over integers, it's iterating over integers because that's what's inside the list. Iter is equal to not new iterator. Instead, we call list.iterator for that. We create an iterate because the iterator exists only because of the list.
Mhm.
Make sense?
Yeah.
And
Yeah.
then from there, while more than one remains, you know, advance case spaces using iter.next, iter.remove, right? That's it.
Okay.
And again, the videos that I have, you can check my my YouTube channel for anything where I go over the linked lists or the Josephus assignment.
Okay.
Because this is an assignment I use this assignment because there's a risk with using an assignment multiple times throughout years, not changing it up. But honestly, I take the philosophy of if it's a good assignment, you should keep it. Because it's a good learning experience. So there's plenty of times I've gone over this on my in my classes, and I've recorded that and uploaded it to YouTube, as I'm going to do for this lecture or for this office hour.